Assalamualaikum and greetings to all of you. I would like to continue chapter 5 part 2. Okay, chapter 5 part 2, surface integrals. Okay, so our objectives are to evaluate the surface integral of scalar and vector fields, evaluate Stokes theorem, and evaluate Gauss theorem. Okay, so our outlines will be 5.1, surface integral of scalar field, surface integral of vector fields. 5.3 will be Stokes theorem, and Gauss theorem. Okay. Okay. So 5.1, surface integrals of scalar field. Okay, surface integral of scalar field. Definition: suppose f is defined and continuous on a surface, let's say sigma. The surface integral of f over sigma is denoted by double integral under sigma f x y z ds, okay, where S is the area of the surface. Okay. The S is the area of the surface. So this S can be, ds can be written as dx dy, dy dz, or dx dz. Also in other way around, dy dx, dz dy, dz dx. Okay, you have to see. Okay, next. Z. Let's say we have z equals to gxy, function of gxy, where r is in the xy plane. So the integration under sigma fx yz ds will be the double integral under region R f x y g function of xy square root dz del z del x squared plus del z del y squared plus 1 still under the square root, and the outside part will be dA. Okay, so remember this formula. Note that z equals to z is function of xy, so we can let s phi or f equals to z minus gxy equals to 0. Okay, del f will be del f over del xi plus del f over del yj plus del f over del zk. Okay, equals to negative gxi minus gyj plus k. Okay, okay, magnitude of gradient f will be square root negative gx squared plus negative gy squared plus coefficient of k will be 1 squared, that is 1. So you may write this as del z over del x squared plus del z over del y squared plus 1. Okay, okay, I just expand from this left and right. Okay, second way, y equals to hxz, where the r in the xz plane, so your integration under sigma f x y z ds will be the double integration under r f x hxz, make sure your function all in xz, z square root of del y del x squared. Let me write again. Z will be square root del y over del x squared plus 1 plus del y over del z squared dA. Okay, let's say your x is function of y and z, where the r in the yz plane ds will be integration of r, your f is function of k, yz, function of yz only, 1 plus del x over del y squared plus del x over del z squared and dA. Okay, we see some example 1 so that you can understand the formula. Example 1, evaluate the surface integral y squared z squared ds, where the sigma is the part of the cone. Z equals to square root x squared plus y squared. That lies between the plane, lies between the planes z equals to 1 and z equals to 2. Okay, so solution. Okay, first you have to sketch. Second, you have to choose the main function. Choose the main function and the dA. Also find the ds. Okay, find the ds. So first we sketch. They said the sigma is the part of the cone. Part of the cone. So, and this is z positive, so just the upper cone. And we have plane z equals to 1 and z equals to 2. Okay. So let me sketch. Here we have cone. Okay, and then we have z equals to 1 and z equals to 2. So z, I should draw a bigger cone so that you can see the planes. Okay, draw a bigger cone. Okay, so what I have now, a cone z equals to 1. So let's say this is 0, 0, 0. So I have z equals to, let's say I put here. So this will be z equals to 1. So I just put another z equals to 2. It's here. I just choose here. Okay, z equals to 2. Okay, actually it can be extend more, so I just choose here. So the cone is infinite, but they give a plane with z equals to 1 and z equals to 2. Okay, so what you can see here, part of the cone that lies between z equals to 1 and 2, which means you have a surface outside the cone, not inside. Okay. Also at the behind. Okay. At the behind, but it is in the outer part. Okay. So, if you project this to xy plane, okay, if you integrate in xy plane, you have to refer the shadow, okay, because we just focus on the surface, we don't want the volume. Okay, don't be confused, we don't want the volume of the cone or the part of the cone that lies between z equals to 1 and 2, but we want the surface. So the shadow of this surface will be at the xy plane. Okay, you may choose YZ plane or XZ plane. For easier case, I just choose XY. But in everywhere you see, you must have a surface. You must see the surface. Okay. So your surface will be a circle here. Let's say I put one circle. Okay, another circle, which is the area. This is surface. Okay. No, this is 2, -2. For extend, this is -2, and this is 2. The behind part will be the -2. The inside one will be 1. Okay. For r equals to 2 and r equals to 1, this is r1 and this is the r2. Okay, so you have to determine the surface which are affected, which is given by the question. Okay, so you have to refer the shadow when the z equals to 1 and 2. Okay, next you already sketch, you already choose the main function, and the dA will be dx dy or dy dx. It's okay. So f is depending on the question, so we choose the xy plane is the area where the z is function of g, let's say xy is function of xy, and then your f should be z minus gxy. So always represent in the implicit form. Okay. Okay, so next we have to find the ds. So ds over dA will be the magnitude of gradient f. So f will be the z minus square root x squared plus y squared equals 0. Okay, so I took this from this formula. Okay, from this cone function. So f will be z minus square root x squared plus y squared. So you have to choose a function, the main function. So this is the main function. So the main function will be the square root x squared plus y squared. So del f or gradient f will be fxi plus fyj plus fzk. So your del f will be equals to, if you differentiate with respect to x, you will have half, and then x squared plus y squared plus y squared. So half bring down, and then we minus 1 will have negative half. Differentiate inside respect to x will be 2. 2x, and the whole thing will be under I component. The same thing, okay, and then we have half x squared plus y squared. Okay, I'm sorry, we have negative here. We have negative here. We have negative here. So differentiate this. We have a negative for the original part. Okay. Half 2yj. The last one. If we differentiate this respect to z, z will be 1. Differentiate this will be 0 because no function of z. Okay. When you differentiate this with function of x, will be, this will be 0 and this will be negative half, and then the power will be minus 1. Differentiate inside with respect to x. Same for y, and then for k component will be differentiate f with respect to z. You get 1. So simplify this, you will get negative x over x squared plus y squared I plus, or we can say minus, we can put minus because plus minus will be minus, minus y over square root x squared plus y squared j, and plus k. I should put k here. Okay. So ds will be magnitude f dA. Okay, remember again, del f del z will be 1. Okay. So square root of x over square root x plus y squared plus negative y over square root x squared plus y squared plus 1 squared dA. And then you can simplify this. You will get square root of 2. Okay. dA. Okay. Then we have not finished yet. So from the question, y squared z squared, and we have here ds. So ds will be substitute as square root 2 dA. So this is, I just choose in xy plane. So the surface in xy plane. So thus the z squared must be in the xy term. Okay, remember, because I have choose the region dx dy or dy dx or in xy plane, so I have to substitute this z in terms of x and y. So we know that this is double integral at xy plane. Thus z equals to square root x squared plus y squared from the cone will be substituted into this equation. So you will get integration of y squared square root of x squared plus y squared, another squared, square root 2 dA. This square root 2 can be taken outside, to outside. So you will get y squared, this is square root 2, and this will be x squared plus y squared dA. So So we have to find the limit. Okay, and then because the region is the circle, so I can use the polar coordinates. So remember your chapter 3 part 1 and part 2, so that it is easy to do this chapter. Okay, it will make easier. So I just draw again r equals to 1 and r equals to 2. Okay, I think r equals to 1. Okay, r equals 1, r equals to 2. Okay, so this is r1 and we have r equals to 2. So the area is outside because it's in between. So the angle for sure it is from 0 to 2 pi. Okay, theta is from 0 to 2 pi, and then your r should be 1 to 2 because we want this area, this part. So r equals to 1 to 2. So your r equals to 1 to r equals to 2. So now you can integrate. This is square root 2. So this is r dr d theta. Remember, for your syllabus, don't change the dr d theta. So just choose in this way. Don't use r d theta dr. So this integral will be from 0 to 2 pi. And then your r will be 1 to 2. So this function you have to substitute with x equals to r cos theta, and this y will be r sin theta. So this will be r squared sin squared theta, and this will be r squared. X squared plus y squared will be r squared. Okay, remember this. So try to do by yourself because you have learned in chapter 3, and then you will get 21 square root 2 over 2 pi. So this is your surface integral. Okay, if we see some example 2. Okay, we see example 2. Example 2. Evaluate double integral under sigma x squared z ds, where the sigma is the portion of the cylinder. Sigma is the portion of the cylinder. X squared plus y squared equals to 1 between z equals to 0 and z equals to 1. Okay, so first thing first, you have to do, you have to sketch. Okay, to see where the surface. So sketch. Okay, so this is nothing but cylinder. Okay, it is circle and it is lift up on on z axis because z is missing. So if I draw, okay, 1 with radius 1, so just choose 1, okay, and then I just lift up, so I just draw another one, and then it will become a cylinder. And then z, between z0 and z equals to 1, so this is z and this is x and this is y. Z equals 0 and z equals to 1. Can you see? So z is 0, for sure it is here 0, I mean in xy plane, x, y, 0. Z 0 means every x, every y, but the z is 0. Okay, z equals to 1 means every x, every y, z equals to 1. So to find the surface, you have to see, you cannot see in xy plane. Okay, you cannot see in xy plane because it is constant and cannot find the area. You can't find the area, but you can see in yz plane or xz plane, which means if you see here, you can find a rectangle. Another one you can see in a sideways, which is one here, and then it is intersect here, one, so another one is here, and one, I mean the radius one. Okay, so either in this side or in this side. You see, okay, so z equals to 1, it is here. Okay, we cannot see the surface area on xy plane, thus we have to find, because try to imagine that this cylinder is hollow. We want the surface, so the surface should be the outside. Okay, and the surface also must be between z0 and 1 for sure. So you have to put your eyes either here or you have to put your eyes here. You can't find any surface if you put your eyes here, which means this is xy plane. Okay, and just draw eyes to see. Okay, so for I just choose yz plane, you can choose xz plane also. So yz plane will be, this is yz plane, so I can draw a rectangle. Okay, and this is z, y, and -1 to 1. Okay, yz plane. Okay, so we have the formula x squared plus y squared equals to 1. So x will be plus minus square root 1 minus y squared. Okay, so I just choose x. I choose x equals to plus minus square root 1 minus y squared to simplify the integral. So let's say I just choose x equals to square root 1 minus y squared, one side. Okay. Okay. Then to find the ds, because I have to find the function first, then to find the ds, f equals to x minus 1 over y squared. So this is in implicit form. I have to do, and then I have to find the gradient. Okay. Okay. So you may ask how I find why I choose x equals something, because x is missing here. Okay. Then del f will be del f over del xi plus del f over del yj plus del f over del z k. Okay, so del f will be, differentiate f function of x will be I, because it will be 0, and del x will be 1. Then this will be minus half 1 minus y squared, negative half, differentiate inside with respect to y, negative 2y, plus, so del f del z, no z here, so 0k. Okay, so this can be cancelled, negative will be positive. So ds is gradient f, norm of gradient f, or magnitude of the gradient f dA. So this is square root 1 squared plus y over square root 1 minus y squared plus 0 squared dA. And this can be represented as 1 over square root 1 minus y squared dA. Okay. Okay, we already find the ds, so now you can integrate this. Okay, so this is nothing but integration x squared z, and this is 1 over 1 minus y squared dA, and for both sides I have to times 2 because we have only one side. I just choose one side first from here, so for other side I have to times 2. Okay, remember this is both sides. Okay, also we have x is function of 1 minus y squared. Okay, x is 1 minus y squared from here. Okay, because we already choose our ds will be yz plane, so we don't want any x there, so we eliminate the x, we substitute the x, so that the function just remain on yz function only. So will be 2 1 minus y squared square root, and then we have squared because of this z 1 over square root 1 minus y squared okay. So if we integrate this, and then we have to find the limit. So this is dA, so I just choose dy dz, double integral, and then you'll have only 1 over square root 1 minus y squared. Okay, and then I just choose dy dz. So from the rectangle, dy dz, which means cut at z, so dy dz, so your z from 0 to 1, your y is from -1 to 1. Try to see back. So y -1 to 1, your z from 0 to z equals to 1. Okay. Okay. So make sure your limit is correct, so that you can perform the integration. Okay. I have z here, sorry, z. So we have z here, so I have to put the z here. And then let me check again. Okay, let me check whether this is correct or not. Okay, so this can be cancelled off. You have 1 minus y squared z over square root 1 minus y squared. So we have 1 minus half will be half, so the square root should be above, and then you remain the z. So you can't integrate this directly. You have to let y equals to sine u and dy equals to cos u du. Also you have to use the sine squared u plus cos squared u equals to 1. So cos u will be square root 1 minus sine squared u. Also cos squared u equals to cos 2u plus 1 over 2, and sine 2u equals to 2 sine u cos u. So this is 2y 1 minus y squared, because I let y equals sine u. So u equals to sine inverse y from this. Okay, so you can do it by yourself, and then you will get pi over 2. 2 times pi over 4, and then you will get pi over 2. Okay, I leave it to you. The next will be surface integral 5.2. Surface integral of vector field. Okay. For a general surface sigma in space, each element of the surface has a vector area ds such that dx equals to n cap ds, which means normal. Let's say we have a surface under a certain domain sigma, so we have a surface ds, and then it's normal. its normal to the surface will be the n. Okay, n. Okay, so let's say we have a force that pushing the surface area, that is F pi plus Qj plus R K. Okay, so if F, I think we don't have any vector here, F equals to P comma Q comma R is a continuous vector field, vector field on the oriented surface sigma with outward unique normal vector, and then the surface integral of F is a continuous vector field on the oriented surface sigma with outward unit normal vector n cap, then the surface integral of F over sigma will be integration under F under sigma F dot ds will be integration of sigma F dot n cap unit normal vector ds, where n, this is just over sigma is, okay, where n is the outward unit normal to the surface. So we obtain the unit normal vector to plus minus gradient phi over, okay, and the ds will be magnitude of gradient function dA. Okay, so sometimes this phi is equals to F. We just, is a dummy variable, we can use any letters. So from the theorem we have, let sigma be a smooth surface of form Z equals to gxy and y equals to head function of xz, and or x is function of y z, and let R be the projection of sigma on the xy plane xz plane and yz plane respectively. Suppose that the surface can be rewritten as phi equals 0 if phi is continuous on R, then one f dot n cap ds equals to integration of f dot the gradient phi dA. Okay. If the sigma has the positive orientation, and number 2, integration f dot unit normal vector will be equals to function r f dot negative phi. Okay, dA, where the sigma is the negative direction. Okay, actually we substitute this into here, you will, and then the ds with this, you can cancel off the magnitude. You can cancel off the magnitude, you will left with nabla phi, gradient of phi times with dA. Okay. Okay, we see some example so that you can understand. Okay, example 3. Let sigma be the part of the surface of the cone z equals to square root x squared plus y squared from z equals to 0 to z equals to 1. Let f x y z equals to I plus T plus K. Evaluate evaluate double integral f dot n ds. So straight away, first you have to sketch. Okay, solution, you have to sketch. Okay, we know that z is equal to positive square root, which means you have a cone that is pointing on z-axis upward, and then now we have to determine the n. Okay, so what do we have? We try to draw first. Okay, So we have a cone. Okay, then this is Z, X and Y. So as usual, the shadow of the cone is on XY plane. The shadow of the cone on the XY plane. Okay, the surface in XY plane. We have what else they give? Z0 and Z equals to 1. So Z0 is here, and let's say I put Z equals to 1 is here. Okay, as in question, Z0 and Z1. Okay. Okay, this is Z, and then this is positive Z and negative Z, and then we have Z equals to square root X squared plus Y squared. Okay, look from the top of the surface for XY plane. So the end should be pointing downwards. N, negative N. Can you see? So when you look from top, the N is pointing downwards. Okay, from the positive Z to the negative Z, the unit normal. So the surface of the cone project to the XY plane. Okay, so we have integral of sigma f dot n ds will be double integration of the sigma f dot negative, okay, negative phi dA, and our dA is on XY plane. Okay, the surface on XY plane. So we have to find the negative gradient. Okay, so remember the theorem, you can do step by step to get the gradient of phi. So you have to find the main function. The main function equals to Z equals to square root X squared plus Y squared. So you can let phi equals to Z minus, you bring to the left hand side, squared plus Y squared. Okay, like usual, like before, these are implicit functions, and then you have to find the gradient, which is phi xi plus phi yj, the same as del phi del y, del phi del x, plus phi zk. So if you differentiate with respect to x, and then you will get negative x over square root x squared plus y squared I minus y over x squared plus y squared, and then we have 1 k. So we want the negative phi because the unit normal vector is downward. So this is just the gradient phi. So negative gradient phi will be x over square root x squared plus y squared I plus y over square root y squared plus x squared j, x squared plus y squared j, plus this time is minus, sorry, j plus minus 1 k, or just minus k. Okay, so we already know that our region is on XY plane. So we have to find the limit also, but before that we just find the negative phi, and then we have the dot with f. So then we have to know what is the f. Is the f is given? Yes, f is given. Okay. So f is given. So f dot negative phi, negative radian phi, because it is in formula, because it is in the formula here. So f dot negative phi will be I111 dot with x over square root x squared plus y squared, comma y over square root x squared negative 1. Okay, so you will get x over x squared plus y squared plus y over y squared, and then 1 times the 1 will be negative 1. So next we have to find the limit. So we know that our dA is on xy. I just put xy denote as the xy plane, not differential equations. So this is dr d theta. Why? Because the region is circle. Okay. Okay. So I know that this circle, if I draw the region again, so this is just R0 to R1, z equals to 1. So the angle is 0 to 2 pi, R from 0 to 1. So what I have here, integration 0 to 1, 0 to 2 pi, and then this x should be r cos theta, and y equals to r sin theta. Also x squared plus y squared equals to 1 r squared. So I have substituted all of this because the formula itself is f dot n cap, and we represent as f dot negative radian phi. So I substitute x with r cos theta, y equals to r sin theta, and x squared plus y squared will be r squared, x squared plus y squared will be r squared, and then what I have is now r cos theta over r sin theta over r minus 1 r dr d theta. Okay, so this r can be cancelled, and then if you solve, you will get negative pi. So now your surface integral under vector field ds is negative pi. Okay, next example. Example 4. Evaluate double integral f dot n cap ds if the f is 2x 2y 3z. Okay, and the sigma is the surface of paraboloid. Surface of the paraboloid z equals to 4 minus x squared minus y squared above the xy plane. Okay, so first you have to sketch so that you can see. if you see 4 minus something, which means it is a maximum curve. So okay, let me draw first 3D diagram, and then this is 4. So make sure you already know how to draw. We've learned this in chapter 1, chapter 2, and chapter 1 and chapter 3. So if I see this is the radius 2. Okay, if Z0, this is circle with radius 2, and then I can put here 2. Okay, then I have 4 here. We get the parabola. Okay, so I know that the surface is outside. The surface is outside. Okay, and then I have to find whether it is positive n or negative n. Okay. Okay. So first, the shadow is on XY plane. Okay, on XY plane, and then the n is upward. Okay, the n is positive upward, positive k, positive z, and positive n. Okay. The surface direction is from the surface to the z positive, upward. Okay. Okay. So the shadow of the plane will be xy plane. So I have radius 2. Then the angle 0 to 2 pi. So you have to find the phi. The phi is z minus 4x 4 minus 4 plus x squared plus y squared. So I just rearrange this function and make it 0 and equals to phi, the phi function. Okay. So the gradient phi will be 2x I 2yj plus k. Okay, remember the formula fxi plus fyj plus fz. Okay. So we have to evaluate. N cap ds double integral. Okay, let's say I put r. Just put r, and then I have the function 2x dot comma 2y 3z. This is the f function. Remember the f given, f dot with, remember the formula, f dot with positive gradient phi. The gradient phi will be 2x 2y k 1. Okay, 1k. So your dA will be the region at xy. So if you solve this, you'll get 4x squared plus 4y squared plus 3z. Remember, we are evaluating for xy plane, region at xy, so we don't want the z. So the z must be substituted with 4 minus x squared minus y squared. So if you substitute this, just put xy for the notation. Get 4x squared plus 4y squared plus 3 4 minus x squared minus y squared dAxy. So they will end up as if you simplify this, you will get x squared plus y squared plus 12 dA region xy. So because of the region is circle, we can convert this into polar coordinate. So your dA will be r d theta, x equals to r cos theta, y equals to r sin theta. So the radius 0 to 2, 0 to 2 pi, okay, because of the circle. And then we have r squared plus 12 r. Okay, try to do by yourself. I just simplify it for you, and then integrate this, you will get 56 pi. Okay, so you can do more example. So I will stop here. I will move in the next class about Stokes theorem 5.3, Stokes theorem, and 5.4 Gauss theorem. Okay, goodbye.